Oh dear. So George, the other night, were you up there? You were just up at the school to receive an award, but you were not graduating?
Yeah, I still have to pass that one test,
Okay. Okay, very good.
but that was
Very
the only
cool.
thing that's the only thing that's in the way.
Okay.
But I will be back in the fall to take a couple more classes since I got the scholarship,
Okay. Cool.
and then I have an application to go to.
A which? I'm sorry, you cut out.
I said I have a application for brain nursing.
I don't know if it's you or me, but I'm barely hearing you.
Can you hear me out?
Volume is very low, George. I don't know what the deal with was. You started out okay and then your volume dropped off.
Is that any better?
That's much better. What'd you do?
Okay. I have some little device on my headset. I just turned it up a little. There's a knob that has a plus and a minus.
Yeah, you keep disappearing. You just disappeared again.
Oh,
I
yeah.
can I I can hear you back there, but
It might have something to do with my internet connection. I'm on a wireless.
I don't know. It doesn't sound that way.
Huh. Well, it's an older laptop. Maybe that's going. Who knows? Anyways, I was saying I've applied to Glen Mercy College.
All right. While we're waiting for the rest of these guys to come on, how strong do the two of you feel about binary conversions?
I'm good with it.
Okay. How about converting binary to hex, George?
Well, I haven't done any of it in years. I mean, I had all this back when I was taking assembler back in '75.
Okay.
But, you know, that's probably for you.
Okay, so Ken, you could use a little help with binary to hex. And actually, it's really very easy. The thing that we have to remember with binary to hex is that every hex value is equivalent to 4 binary digits. Okay? So if I go through and I'll and what I'm doing is I'm putting in hex values here. And if you memorize this, you see how, Ken, I just counted from 0 to 16, if you will, in decimal. And I'm showing the hex values and then the binary values. Yes, thank you. You are correct. So if you remember these patterns, that an F is equal to 4 ones, that an E is equal to 3 ones and a 0, and so on down the line, if you can remember that, then binary to hex is really very easy. And to do a binary to hex conversion, all you need to do is you just take your binary number. So I'll lay out a couple of numbers here. So there's my binary number, and in parentheses I'm going to put the base just to make sure that everybody understands what type of number that is. And what you then do is you then take your number and you start basically splitting it off into groups of 4. So you've got a group of 4 there, a group of 4 there, and a group of 4 here. You'll notice that this has a leading 0, and for the time being that we're going to want to keep that there. So as we look at this group of 4, 0, 1, 1, 1, 1, we'll notice that it is up here and it is equivalent to a hex 7, and we'll put that in. Oh, sorry. Oh, that's it. Our next one is, when we look at that pattern, is a 0, 1, 1, 0, which is equivalent to a 5. And then finally, our last group of 4 is equivalent to a 9, and that's base 16. So our answer is 7, 5, 9, base 16.
Isn't it 7, 6, 9?
Oh, God. Yeah, you're right. Thank you, George. 7, 6, 9. Okay, does that make sense? Now going the other way, to take AEB, each hex digit is equivalent to 4 binary digits. So we've got our first A, then we've got E, and then we've got B. And there's our answer there. What was that, Ken? Very, very what? Oh, I understand very well. Okay. Okay. Now, does this, Ken, make sense to you, going from hexadecimal to binary? Okay. The real challenge in any of this is going to decimal. And, you know, quite frankly, I find it's the easiest way to go if you're converting decimal to some other value, whether you're converting decimal to binary or you're converting decimal to hex, is to always convert decimal to binary first and then go to hex. If you've memorized what we did above with the 4 binary digits equivalent to 1 hex digit, that process is pretty easy. But if you have to make a choice, if you have to get from binary or from decimal to hex, the easiest way to go is to go to binary first, then go to hex. Okay? And really, in order to do that, you have to have, you have to know your powers of 2. Now, we already know that anything to the 0 is equivalent to what? What was the rule we used last week?
1.
Correct. Anything to the 0 is 1. So I'm going to put in the power, and then I'm going to put in the value. So then 2 to the 1, anything to the 1 is going to be
the number you're raising it to.
Okay.
In this case, 2.
Great. So 2 gives me 4, 3 gives me 8, 4 gives me 16, 5 gives me 32, 6 gives me 64, and 7 gives me 128. All right. So I've got a number, let's say 123, base 10, and I wish to convert it to whatever its equivalent value is, base 16. What we have to do is we have to take our powers of 2, the different values that we see here, And we have to then subtract those out of the 123. So looking at my powers of 2, I notice that 128 is bigger than 123, so I can't use the 128. I can definitely use the 64. Okay? Well, let's do it this way. I can't use the 128, so I'm going to have basically a 0 here, and I'm going to just put in 128 just to note the value. The 64 I'm going to use, and if I subtract the 64 from the 123, I've got 59 left over. Now, can I subtract 32 out of the 59? I can. And I'm going to take the 32 out of the 59. And that's going to give me 27. Now, can I take a 16 out? Yes, I can. And that's going to give me a 9. Or I'm sorry, that's going to give me an 11. Next, can I take an 8 out? Yes, I can. And that's going to end up giving me a 3. Now, can I take a 4 out? No, I cannot, because the 4 is too big for the 3. So I'm going to put in a 0 for the 4. Next, we'll take out a 2. Can I take that out of the 3? Yes, I can. And that basically brings me down to 1. And can I take a 1 out? Yes, I can. And that's going to bring me to a 0. So the result of our 123 base 10 to right now, our binary number is 0, 1, 1, 1, 1, then 0, 1, 1, base 2. Now I'm going to take that and as we said before, going binary to hex, I'm going to break it up into 4s. And when you break it up, you always want to chop up right to left. So we're going to go and as you can see, I've got a hexadecimal, I have 0, 1, 1, 1, which is equivalent to a hexadecimal 7. And I've got a 0, 1, or a 1, 0, 1, 1, which is equivalent to a B. So my answer is 7B base 16. How's everyone doing with that? Okay, very good. When we do the conversion to IP version 6, it's going to be very important that we understand how to do this because you'll have to be able to convert the IP version 6 IP address is in hexadecimal. So we still have the games that we play with binary and so on as we change addresses and so on. We don't have the subnetting problems that we do with IP version 4. But still, it's very good to understand how to jump from either binary, decimal, or hexadecimal. Okay? And again, if you're going from decimal to hexadecimal, go to binary first. The same is true for going from hexadecimal to decimal. And let's just go through that. So I've got hexadecimal to decimal, and what I'm going to do is I'm going to do basically C9 is the hexadecimal value. I'm going to convert that first into binary. And what we're going to have is basically 1100 space 1001. Now, as we look at this value in binary, and I'm going to put it together, what I do is I just start looking at the ones. So I know the first one is 2 to the 0. So that's going to give me a 1. And I'm just going to write that down. My next value, which is a 0 though, is actually 0 times 2 to the 1. And 2 to the 1 is equal to 2. But times 0 gives me nothing. 2 to the 2 is also 0, so that's not going to give me nothing. Then we've got 2 to the 3, which is going to give me an 8. 2 to the 4 and 2 to the 5 aren't going to give me anything. Then 2 to the 6th, which is equivalent to a 64, and then 2 to the 7th, which is equivalent to a 128. So I've got 192, I've got 200, and 201. If I add all of those up, wait a minute. Oh, shoot.
It's 193, isn't it?
Yeah, 1 second. No, I'm still getting 201, George. 128 plus 64.
No, you're right. You're right. I didn't see the 8. I'm sorry.
Okay, no problem. How does that sit with you there, Ken? Super. All right. So again, when going from decimal to hex or hex to decimal, always go to binary first. It's easier to convert. And again, the biggest thing you've got to remember is this little table right up here. If you can remember that, it's really a piece of cake to go between the different bases. All right. If there are no other questions with respect to this, I'm going to leave. That will be my math portion for tonight. Next week, we will talk about actually start getting into some of our subnetting. All right. So tonight we're going to review some of the topics in our Chapter 2. And essentially we're going to begin by talking again about the OSI and the TCP/IP models, talking about cabling and cabling types, and I'm sure this is going to be a review for like the 5th time for you guys, so just hang in there. Talk about the technology and media access control, explain network segmentation and basic network management concepts, and then select the appropriate media. So to start off with, is Ethernet is basically a contention media access method that allows all our hosts on the network to share the same media. What do we mean by contention media? Okay, wait a minute, Ken. Wait 1 second. Is the purpose of this to figure out IP version 6 addresses from IP version 4? Yes, is to basically be able to break down the bit combinations in an IP version 6 address, because there are certain switches that are actually set at the bit level. although most of the categories for IP version 6 are right at the hex level, so and there's no need to convert to decimal. But there is the possibility where you're taking an old IP version 4 address and you're converting it to an IP version 6. Okay, Ethernet is a connection media. No, they're talking about contention rather than connection. What's the difference? What do we mean by contention? Well, basically contention means, okay, challenge response, not so much. Basically it means you've got to fight to get to be able to transmit, that you must share this resource with the other devices that are connected to the network. So when we look at Ethernet in its simplest configuration, and that being where host systems are attached via hubs, okay, it is every man for themselves. The first one out there to get access to the line basically wins. So there's some contention that is going on between the different hosts in order to access or to have permission to transmit on the Ethernet cabling. Now, as they show, Ethernet is probably the most popular for a couple of reasons. First, it's relatively easy to integrate with new technologies, as they say, such as fast Ethernet and Giga Ethernet. But it's also relatively inexpensive when we take a look at the wiring media, and then we look at the devices themselves. Way back when Ethernet was really coming on strong, it was competing with Token Ring. And the problem with Token Ring, although it had certain advantages over Ethernet, the problem with Token Ring was that it was, for the most part, proprietary due to IBM. IBM had patents on Token Ring devices. So anytime you wanted to buy a Token Ring network adapter, you had to pay a premium price to have that adapter. And it was that reason, I think, more than any other, that really drove people to look very hard at Ethernet, even though Ethernet technically was not as strong as Token Ring. But the weaknesses that early Ethernet had were soon resolved with the implementation of both fast Ethernet and switching. Switching basically solved the big problem, namely collisions that we were having within the Ethernet environment. The last point here is that it's easy to implement, and troubleshooting is relatively straightforward. Again, if you use the Ethernet, the oldest form of Ethernet, such as using ThickNet or ThinNet, these were both coaxial connections, and you use the bus. Sometimes troubleshooting could be a problem. Okay, trying to run down what station or what connection was creating the problem could be a real nightmare. And this really depended on how long the cable connection was. In a bus configuration, the cable runs from one system to the next, to the next, to the next. So it's essentially a daisy chain. Any break in the daisy chain is going to cause the entire system to more or less fail or to have problems. In later implementations of Ethernet, we used a star configuration. And we first saw the star configuration when we were using hubs. And we all know that with a hub, I have separate lines that run from the hub out to each one of the hosts. And a host could be a workstation, it could be a printer, it could be a server, what have you. but there was a separate line that ran out to each host. So because of that configuration, it was very easy to troubleshoot and identify where the problems were. The problem with the hub is that the hub worked very much like the bus in that everyone was in the same collision domain. And that's why we would often say that when we look at the different topologies, that even though Ethernet, when using a hub, had a star topology, it still acted like a bus topology in terms of its logical performance, okay? And that everybody heard the traffic. Again, all of this changed when we started implementing switches. Let me just turn on the presentation here. And move something around here. Okay, there we go. That's better. So, again, Ethernet is a contention-based media system. Specifically, we use CSMA-CD, which is collision sensing media access and collision detection. Now, here we see that both host A and D attempt to transmit at the same time, and that creates a collision. You'll also notice that we're using a bus here. This is a bus configuration, and that's the way the early Ethernet networks worked. When that happens, as soon as we have a collision, what happens is the systems send out jamming signals to basically clear the line and make sure that nobody else is going to transmit anything, so as not to be confused with the two packets or the two frames that just collided up above. So that's why we see these time clocks here, is that they're waiting. And they're waiting for random periods of time before they attempt to retransmit their packets again. As we said in the early Ethernet days, everything worked like a or a logical bus. Whether you're using a hub or you're using a bus connection, everything ran like a logical bus. And for that reason, because it was a bus, because everyone belonged to the same collision domain, Ethernet was only capable of transmitting at half duplex. In other words, only one direction at a time. You couldn't have two-way simultaneous communication going on because that would have simply have created collisions. In the early Ethernet networks, okay, only one system could transmit at any given time in any given direction, not two directions simultaneously. Okay, Cisco says it's using only one wire pair with a digital signal running in both directions on the wire. But only at one direction at a time. Okay, and that's where I think they're saying uses only one wire pair. All right, later on, when we converted to switches, we were then capable of transmitting at full duplex. In other words, two directions simultaneously. In order to do this, Ethernet had to use both pairs of wires simultaneously rather than one pair at a time. Again, full duplex also requires that we have a point-to-point connection between a transmitting device and a receiving device, specifically between a switch and a host. We can use full duplex Ethernet in the following three situations: between a switch and a host, in other words, between a switch and a printer, a switch and a PC, a switch and a server, what have you. We can also use full duplex between a switch and a switch. And finally, we can use full duplex between two hosts. between two PCs, a PC and a server, a PC and a printer, we can use full duplex. Now in this, when we use this configuration, there are no switches, okay? But we do have to use something called a crossover cable, and we'll talk about the different types of cables here shortly. Okay. All right, gang. Give me a second here. I didn't grab anything to drink before I started. 1 second. Okay, just grab something real quick out of the refrigerator. Okay. Does 802.3 define only half duplex, or does it include both half and full duplex? Okay, we're going to look at that in just a second, so hold on that question, Ken. All right, before we get into the different protocols, and specifically layer 2, the data link layer, and its sublayers, let's first talk a little bit about Ethernet addresses. Ethernet addresses are often referred to as MAC addresses or hardware addresses. And these are essentially 48-bit, 6-byte, where a byte is equal to 8 bits, addresses, and they are written in a hexadecimal format. Often you will see them written as digit, digit, colon, digit, digit, colon. So it's, 2 hexadecimal digits separated by a colon. So in this, notice you'll see that we've got 48 bits, but we only show 47. Keep in mind, all right, that they're probably counting by 0. So bit 0 through bit 47. All right, which gives us our 48 bits. So I've got an IG, an GL, the organizational unit, which is essentially the ID that is assigned to the vendor. Okay, so every networking vendor that produces, Ethernet cards or produces switches, they're going to have an ID assigned to them by the IEEE. And then finally, the remaining 24 bits, or 4 bytes, are reserved for, 3 bytes, are reserved for assigning to ports on either on network interface cards or on switch ports or other Ethernet ports on other devices. All right. So again, we go back to this chart where we're memorizing some different values. And again, we'll get into this this particular conversion chart a little later on. I'm not going to worry about it right now. All right. So now, this is the answer to your question, Ken. Okay? And it really depends on what type of cable was being used. Okay? Very early on, the very early versions of Ethernet, essentially it was one large chunk that handled both the data link layer as well as the physical layer. And when we look at the data link layer, we're talking about the MAC layer in this particular case. What happened is later on, this was original Ethernet. We then got into 10-base-2, 10-base-5, and 10-base-2 was your thin Ethernet. 10-base-5 was your thick Ethernet. 10-base-T was the first definition for twisted pair, and it only provided 10 megabits of bandwidth. Now, this could be used in both in some implementations, you could use this both as full duplex or half duplex, depending upon the device that it was plugged into. 10 base F was a fiber implementation, and then later we got into 100 base T or 100 TX or 100 base FX, which was fiber, or 100 base TF. And if I recall correctly, TF was something that was implemented by HP. And what was interesting about this particular type is that it used all 4 pairs of wire. In an Ethernet twisted pair installation, there are 4 pairs of wire. However, in most of them, in the 100 base T, okay, we only use 2 pair of those wire. We do not use the other 2. In the 100 base T4, we use all 4 pair. And honestly, I don't recall what the wiring was for all 4 pair, how they use that. But you rarely see that implementation, okay? The one that you're most often going to see is the 100 base TX or the 100 base FX. Now, up above we implemented something called 802.3. And this was a protocol that was common to all of these things down below, which had more to do with the physical type of media. 10 base 2 being an RJ58 type cable. 10 base T was an RG11 or RG8 type cable. And that was your thin Ethernet and your thick Ethernet. And then the 10 base T, that used a category 3 twisted pair cable. But all of these different cabling types shared the 802.3 protocol. And again, some of them provided for half duplex and full duplex, but it really depended more on the type of device that you were connecting to. Now, in a 10 base 2 or 10 base 5, there was no way that you were going to be able to have full duplex. It was only capable of doing half duplex. And when you think about it, look at the construction of a coax cable. A coax cable only has 2 conductors in it. Unlike twisted pair, where we actually have 8 conductors altogether, we use 2 pair or 4 conductors. So in the 10 base 2 and 10 base 5 with only 2 conductors, it's, physically, it's only possible to use half duplex. Does that make sense, Ken? Super. All right. So, cabling is an important discussion, especially if you're planning on taking the CISC exams, and I most definitely agree with that. There are, therefore, 3 Ethernet cables that you need to be familiar with. And really, only 2 of them are what I would describe as Ethernet cables. The first is a straight-through cable. And this can only be used in certain locations. The next is a crossover cable, where we're crossing 2 pairs. And then finally, the third cable is a rolled cable, and that is generally used for special connections, specifically console connections. If you're connecting to the console port on a switch or a router. So let's look at the different cables. A straight-through cable. First, notice what pins are being used. 1, 2, 3, and 6. There are 8 positions altogether, but I'm only using 1, 2, 3, and 6. So on a straight-through, 1 to 1, 2 to 2, 3 to 3, 6 to 6. This particular type of cable can be used for a host going from a host to a switch or a hub. It can also be used going from a router to a switch or a hub. Okay? Next, crossover cables. Okay? Again, you will notice that we are still using the same pins, okay, or the same connectors, 1, 2, 3, and 6. 1 and 2 would be described as pair 1. 3 and 6 would be described as pair number 2. Unlike the straight-through cable, you'll notice that pin 1 on the left connects to pin 3 on the right. Pin 2 on the left connects to pin 3 or pin 6 on the right. And then 3 on the left to 1 on the right, and 6 on the left to 2 on the right. And the reason for this is that if we focus on the left-hand side here, and if I can get my pen to work, here we go. If we focus on the left, essentially what would happen is the first pair might be described as the transmit pair. And the transmit pair would always talk to the receive pair. Going back on the left again, if these two are the transmit, then these two are the receive. And if these two are the receive, then these two over here are the transmit. Okay, so this is what we mean by a crossover cable. For the most part, okay, switches are able to figure out automatically whether you're using a crossover cable or a straight through cable. They will get it all figured out, okay, and they will make the appropriate connection, making sure that the transmits are plugged into the receives and the receives are plugged into the transmits. Cisco, however, rather than giving intelligence to their Ethernet ports on their switches, however, has left it such that you've got to be aware, you've got to use a crossover cable if you go from a host, namely a PC, directly to the router. You've got to use a crossover cable. If you go from a hub to a switch, you should use a crossover cable. A host to a host, you should use a crossover cable. And again, a switch to a switch, you should probably use a crossover cable. Again, many switches have become intelligent enough to figure this out. However, for the test, you should remember the following. When going switch to switch, hub to hub, host to host, hub to switch, or router to host, use a crossover cable. Okay? All right.
Isn't there an association with, like, negative and positive charges for these?
Yes. That is correct, George. For instance, we might have a, for instance, this T. Hold on a second, guys. Let me just take this. George.
Yes.
I'm good. How are you? Okay. Is everything okay? I'm good. But listen, I'm in a class right now. No. So let me. Well, I'll tell you what. I'll give you a call later tonight if you don't mind. Okay. Okay. All right, I'll give you a call tomorrow. All right, George. Have a good night. Thanks. Bye. I think you were saying, George, that you had George Gleim for math, didn't you?
I'm sorry?
Did you have Dr. Gleim for math?
No.
Okay.
I took all my math courses at Penn State
All right. Very good.
and transferred them.
All right. Well, in either case, that was one of the other professors. So, but yeah, we'll have a transmit plus and a transmit minus, and this goes over to a receive plus and a receive minus. Okay, but you are correct.
And that has to do with electricity, right?
Yes, exactly. What happens is they use a particular voltage level for transmitting the signal. Okay?
Thank you.
Okay. So, moving on. Let me change my pointer here. Now the rollover cable. So as they point out, rolled cables aren't used to connect any Ethernet connections. You can use a rolled Ethernet cable to connect host to router through the console serial port. Now, what they mean by this when they say an Ethernet cable, I don't think they should use the term Ethernet. I think they should use the term twisted pair, a rolled twisted pair. And we use twisted pair for Ethernet for creating Ethernet cables. So I think it's kind of misleading whenever you call a rolled cable an Ethernet cable. A rolled cable is simply a particular pinout for a twisted pair cable. And twisted pair cables have four pairs of wires, giving us a total of 8 conductors. And what we're seeing here is that in a rolled cable, we've got pin 1 to 8, 2 to 7, 3 to 6, and so on down the line. And this is the cable that we typically will use whenever we are connecting our router console port to what on the host? What do we generally connect to on the host? What port? Serial, Ken. Thank you. Okay, very good. So we go from the console port on the router or the switch to a serial port on our host or our PC or laptop. Okay. Whenever we make a connection with a console cable and we're using a serial connection, these are the default serial parameters that we need to use. Specifically, 9600 bits per second, 8 data bits, no parity, and 1 stop bit, and no flow control. Often, whenever you set up programs for serial communications, they often will default to these settings. So you don't even have to memorize these. And quite honestly, I don't ever remember seeing a test question out of Cisco that said, what were the parameters for these? All right. So he's got a couple of questions here. What type of cable are we going to use in order to connect a switch to a host to begin with? For A, what type of cable do I use? Straight through. Correct, Ken. Thank you. So whenever we go from host to switch, we should use a straight through cable. Now, how about when we go from switch to switch? What should I use?
Crossover.
Yes. The proper answer is crossover. But again, if you play with most switches today, you can use a straight through cable without a problem. They will automatically auto-sense the type of cable and they will figure it out. But the answer to this question, switch to switch, we want to use crossover. Okay, now what type of cable would we use in each one of these connections? So again, going from a host to a switch, I'm going to use a straight through. From switch to switch, I'm going to use a crossover. What am I going to use between the switch and the router?
Straight through.
Okay. You can, yes, you would use a straight through cable. Now, how about if we had, in the case of, we have a host over here that's connected to the router. What am I going to use?
A rolled cable.
Why a rolled cable, George? Why not a crossover cable? The key here is the word, okay, because they're not similar. Not quite, Ken. The key is the word console. Console tells us the type of connection that we've got going to the router. And because we're going to the console port on the router, that would indicate that we are going to use a rolled cable. If the word console were not here, and we were to assume that this host was connecting to an Ethernet port on the router, then at that time I would have to use a crossover cable. Okay? All right. All right. So next we want to talk about data encapsulation. And again, this is a process that occurs as data is passed from the higher level protocols, okay, or the higher layers within the TCP IP model or the OSI model. So as data is passed down from the high layers to the lower layers, we encapsulate that information from the higher layer. What are we encapsulating it with? Well, first, let me ask the question, what does encapsulate mean? Well, as the next comment we have down below, it says it's wrapped within the protocol information. So encapsulation means to enclose, okay, or to cover. So what happens is we take the information from the upper layers and we basically enclose or encapsulate that data with additional information, specifically information that belongs to the layer that we just passed it down to. So as each layer receives the data from the layer above, it then encapsulates or it encloses that data with its own information. Then, when information is received on the other end, it is de-encapsulated. In other words, what happens is as the data rises through the OSI model or the TCP/IP protocol stack, each layer peels off the information belonging to that layer for processing of that data packet and then passing that data packet on to the next layer above. So this is the process of encapsulation. So when we encapsulate things, we basically give them different names. And often these names are generically referred to as PDUs, as we see up here, up above, the PDU. So as data comes down from the application layer to the presentation layer to the session layer, it is then encapsulated in the transport layer. And at that point, that encapsulated data, which contains the data that came from up above and now includes transport layer information, that piece of information is now referred to as a segment. And this specifically talks to the TCP/IP model, not necessarily the OSI model. The OSI model doesn't use the terms segment or packet, okay? This refers to TCP. As the segment is then passed down from the transport layer to the network layer, again, it is encapsulated by information used by the network layer. Information in the network layer is specifically IP address information, source address, destination address, possibly some MAC information, and so on. And this encapsulated data at this point at the network layer is now called a packet. Packets are then passed down to the data link layer. And again, the data link layer adds information onto the packet, thereby encapsulating the packet with data link layer information, creating this thing called a frame. Now, we already talked about the addresses that are used in a data link layer in an Ethernet environment, okay? And that would include source and destination MAC addresses, or your Ethernet address, your hardware address. So part of the encapsulating data that's added to the packet that then creates the frame is your Ethernet address. Next, it's not so much encapsulation. The frames are passed from the data link layer down to the physical layer, and it's at this point that the system takes apart the frame bit by bit and transmits those bits out onto the medium. So any type of physical transmission is done via bits. Okay. Any questions?
Where's the datagram come into play in this?
All right, excellent question. Segments, packets, and frames. Okay. Yes, up above, segments, packets, then frames. Now, to George, your question, segments are used in reliable communication. Specifically, we're talking about TCP. Okay? Another type of transmission that we can have at transport is an unreliable transmission. And if we use that, then we use a UDP header rather than a TCP header. So when we use UDP, okay, we no longer have a segment. And we instead have something we call a datagram. Okay? Okay. All right. Are both of you clear on that? Any questions? Okay, very good. Again, what we can see is how, as we go from the upper layers to the lower layers, how we encapsulate the data. We see the segment, again, a TCP segment. Here's the segment, and it is now encapsulated into the packet, which includes a source IP, a destination IP, the protocol, and some additional pieces of information. The packet, including the segment piece, is then passed down to the data link layer, where the data link layer now creates the frame and adds in its information, its encapsulating information. And we have a destination MAC, a source MAC, an Ethernet field, the packet, and the FCS. What is the purpose of the FCS? If you recall, the FCS, error control, correct, Ken? All right, so the FCS allows us to check to make sure that when we receive the frame on the other end, that the frame is complete and that it has not become corrupted. Finally, at the very lowest layer, at our physical layer, okay, our frame is going to be taken apart bit by bit and transmitted out onto the wire. All right. Port numbers. When we talk about the transport layer, and let me just go back. You know, we talked about TCP header or the datagram header or UDP header, okay? Generally, when we talk about these headers, TCP or UDP headers, we're typically talking about what ports are we attempting to address. So, transport layer uses port numbers to identify both virtual circuit and upper layer processes. Often what happens is when we have an application running, we are going to use some very specific ports, okay? In addition to the just the generic ports, we have to identify the source port, what port is this coming from, and what is the destination port on the receiving machine. All right. Now, we briefly talked about the OSI model and the TCP/IP model. The Cisco three-layer model is not an OSI model, okay? It is used to help you understand best practices for designing a Cisco-based network, okay? Or, you know, for that matter, for any type of network. Now, the Cisco three-layer model, in order to build a good high-performance network, calls for 3 layers. At the very bottom, we have the access layers. And you'll notice that the access layers consist of workgroup switches. And this is where we connect our hosts to the switches. And that's why it's called access, because it provides access to the network from the hosts to the network via the workgroup switches. Next, we get into our distribution routing. Now, distribution is primarily controlled by routers and primarily runs in the network layer. The access layer runs in the data link layer or layer 2. The distribution layer runs in layer number 3. Okay? And in this layer, what I'm doing is I'm identifying what is the best route to send my traffic. I'm also using my ACLs to define what traffic is allowed to go where. So there's a tremendous amount of control that is being performed at the distribution layer. In our final layer, in the core layer, the only thing that the core layer is focused on is speed. It wants to get the packets to the fastest or to its destination as quickly as possible. Okay? It doesn't want to do any type of filtering. It doesn't want to use access lists. It's just focused on moving data. Now, what's kind of interesting is that these devices here, okay, are often referred to as layer 3 switches. And a layer 3 switch basically lives in both layer number 2 and layer number 3 of the TCP/IP model. Okay? However, they will often use WAN type connections. Okay? Generally, we don't see a lot of Ethernet up here, or we can use Ethernet, especially for the short range stuff, such as you want to go between two wiring closets or something along those lines. We can use Ethernet, and typically gigabit Ethernet. So these are the 3 layers that we have that we would use in designing a Cisco network, or again, any network for that matter. Okay?
How does this
Correlate to the OSI model.
Exactly, George. It doesn't. It doesn't. Okay? It roughly does. As I had mentioned, the access layer is primarily layer number 2. The distribution layer resides in layer number 3, and the core layer is both 2 and 3.
So there's
No upper layers associated with this at all.
That is correct.
Okay.
When you think about the upper layers, okay, you are thinking about the only time the upper layers come into play is when the device that is connected is a host device. Okay? Here's a question. Do switches care about the upper layers? What layers do switches care about?
2 and 3.
Correct. And for the most part, they're focused primarily on 2, but they do know something about layer 3. Now, how about the distribution layer? What layer, again, is it focused on?
Two.
Actually, the distribution layer is focused on layer number 3, the networking layer. Is there any device in this diagram which would be interested in the upper layers, namely, let's say, transport layer, session, a presentation, or application layer? Are there any devices here that would be interested in the information in the upper layers? The answer?
Apparently.
Go ahead.
Apparently not.
Well, if you notice, take a look all the way on the right-hand side at the bottom. What is that?
Server?
That's a server, okay? Now, the server is at the very bottom of this model, but that really kind of makes the point, is that the Cisco 3-layer model has nothing to do with the OSI model. When we talk about upper layer model, we're talking about the TCP or OSI model, and that's at the top. Well, the server, even though it's at the bottom of this diagram, it's the only device here that's interested in the upper layer of the TCP or OSI model. These other devices here, all they're concerned about is the lower 3 layers for the purpose of getting information around the network. So this model, while we can draw correlations between the OSI and TCP models to this model, okay, this model really does not line up very neatly with either of those.
What
Do the box symbols represent?
Those are our work group switches. Or you mean the ones at the top or the ones at the bottom?
The top.
Okay, those are layer 3 switches. Generally, when we... Go ahead.
Where would a gateway go in the core layer?
Where would a gateway go?
Yes.
Gateways are generally higher layer devices, okay? For instance, you would use a gateway if you wanted to go between a network that was running TCP/IP and a network that was running IPX/SPX. Because the conversion process is going to occur up at layers 4 and 5. Okay?
so
Does that mean that this model doesn't recognize the existence of gateways?
This model doesn't address gateways, okay? Although gateways do play a role in networks, okay? This is a basic network with respect to Cisco. In fact, there are a number of devices that Cisco provides that run in the upper layers. You know, VPN firewalls, for instance. Those are upper layer devices. And, you know, VPNs play a very important role in today's networks, but you don't see them referred to here. Okay. Any other questions? All right. Okay, well, that was Chapter 2. Let's take a look at Chapter 3. Just move some things around. Would help if I clicked on the right thing. Okay, well, let's go with this. Okay, so this is where we get back into talking a little bit more about TCP and the DoD model. Move this back over here. I'm not exactly sure why this says Chapter 2. It's actually Chapter 3. Yeah, it says Chapter 3 here, Chapter 2 here, so who knows. So we're going to talk about the differences between TCP/IP and the DoD models. Very similar. The DoD is older and TCP much newer, and it is what replaced, TCP replaced the DoD. And then we're going to get into our IP addressing classes. All right. So when we look at, to begin with, the OSI model, we see that we've got our 7 layers there, starting with application all the way down to physical. Now, originally what happened was the DoD model was not as refined. It didn't break out some things, and it just lumped them into one big box. For instance, process and application is lumped into one very large box. And do you recall why we break things down into smaller boxes? Whenever you're trying to create any type of system, you want to break it into small chunks so that it's easy to build, it's easy to modify, it's easy to test, and it's easy to debug or find whatever problems we might have. So initially, when you're writing something, there's often this desire to just drop it all into one box, and that's what we saw in the DoD model. They created the process or application portion of the TC or of the stack. But later, when we created the OSI model, we said, hey, look, there are actually, when we look at the process and application box of the DoD model, there are really 3 distinct portions that we need to break this up into to make this a little more manageable. So the OSI said, okay, we're going to break this into application, presentation, and session, and we know that each one of those has a very specific function. Going down the DoD model had host-to-host, and rather than host-to-host, what they were going to simply call this was transport. However, for the most part, it was going to still perform the same function. Then the next layer down on the DoD, we had internet, and again, they changed that to simply network. And then finally, we had network access, and again, the OSI model said, look, we need to simplify this. We need to break this up. So we're going to create 2 separate layers, a data link layer and a physical layer. All right, again, as we look at some of the different pieces here, okay, between the DoD and OSI, we'll notice that some of the things that I've got, some of the different applications I have, Telnet, TFTP, FTP, SMTP, LDP, NFS, SNMP, and X Windows. These are all application layer protocols. Below that, as we talk about the transport layer, we said 2 primary protocols. And TCP and UDP are not OSI models, okay? This is more DoD/TCP, okay? I think to bring up OSI here can be a little confusing. In either case, the internet layer, known as the network layer in the TCP model, we have ICMP, we have ARP, and we have RARP. And then down below, common to all 3, we have the IP, or Internet Protocol, that supports all 3 of these. Finally, we've got the network access. We've got Ethernet, Fast Ethernet, Token Ring, and FDDI. Now, we know that running above all of this, I've got my 802.3, okay? So really, Ethernet is broken into 2 pieces, 802.3, and then, Ethernet, depending upon whether it's, 10 base T, 100 base T, 100 base TX, Fast Ethernet, whether it's Token Ring or FDDI. Again, some of the application protocols that we have within the TCP/IP model, Telnet, and the list. DNS, DHCP, or BootP are some of additional beyond the diagram that we had on the last frame. TCP is a very important application protocol that we have, and it refers to Dynamic Host Configuration Protocol. It is designed to help a host that does not have a pre-configured IP address or other pre-configured IP information to receive that information from a DHCP server, which could be an actual server or it could be a router on our network. Now, the process of getting information, specifically getting a TCP IP address for a host from a DHCP server, has a couple of steps to it. The first thing that occurs is what's called a DHCP discover, which is a client broadcast. So this broadcast is sent out to everyone within the broadcast domain, not the collision domain, but the broadcast domain. The server then responds with a unicast DHCP offer. Now, a unicast is point-to-point. It's sending out this address to a specific machine. Okay? It is not broadcasting it out to the group. Again, the client responds with a broadcast message, and this is referred to the DHCP request. And finally, the server responds with a DHCP pack. Again, it is a unicast transmission. When we talk about networks, broadcasts are the things we want to try to keep minimized. We want to try to keep them to a minimum because broadcasts tend to send packets out to many hosts within the broadcast domain, and all it does is it chews up bandwidth. Anyone know why the system uses a broadcast? Why does the client always respond and many times with a broadcast? Essentially what's happening is the server is basically shouting out to everybody saying, hey, look, whoever's the DHCP server, I need an IP address. So it doesn't know who the DHCP server is. So in order to get the DHCP server's attention, it yells out its need for an IP address out to everybody. Not that everybody needs to hear it, but the client doesn't know who to send this message to. Now, I would say that that's just fine for the DHCP discover. I don't understand the logic in the client broadcast and a DHCP request. You know, that doesn't make a lot of sense. All right. Host-to-host layer. Now, if you recall, the host-to-host layer in the DoD model is equivalent to our transport layer in the TCP IP model or OSI. So the main purpose of the host-to-host is to shield the upper layer applications from needing to understand the network down below, needing to understand IP addresses, needing to understand how things get routed or switched. So, as they say here, this layer says to the upper layer, just give me your data stream with any instructions and I'll begin the process of getting the information ready to send. So it handles all of the complexities and it basically just tells the application layer, just give me your stuff, I'll take care of all the details. So the following sections describe the two protocols, specifically the Transmission Control Protocol, or TCP, and the User Datagram Protocol, or UDP. Here is the TCP header showing the different fields that we have. You'll notice that the header is made up of several fields, okay? And what I would describe as words, okay? consisting of 32 bits, 0 through 31. That's 32 bits. So we have multiple words, and the number of words that are going to be in this thing is pretty much going to be dependent upon how much data we have in our segment or in our datagram. In this case, we're talking about the TCP header, so we're specifically talking about segments. Looking at the very top line, we'll notice that the first 16 bits, 0 through 15, are reserved for a source port. In other words, where is this information coming from? What application is this information coming from? And each application is assigned a specific port ID. Next, we have our destination port ID, and this is the port ID on the transport layer on the receiving machine. Now, one of the things that makes TCP reliable is the fact that it acknowledges its data transmissions and that it checks to make sure that things have been received appropriately without any problems. And to do that, it uses these things called sequence numbers and acknowledgement numbers. And these are numbers that are used in sequential order, serially. And the system is constantly checking the numbers to make sure that a sequence number hasn't been skipped or possibly has been lost. When you get sequence numbers out of order, okay, this can indicate that there may be some sort of loss of data. In addition to our sequence and acknowledge numbers, we have some other control information such as the header length, and this describes how long this entire thing is going to be. Okay? Now, if it's only 4 bits long, okay, what is that indicating? If I only have 4 bits, that tells me the value, I can only have a value between 0 and 15 decimal. So probably what's happening is it probably says how many words, how many 32-bit words are going to be in here. The reserved block, 6 bits, is used to hold different types of values. The details are not extremely important. And then we have our code bits. And then finally our windowing bits. And we had talked about windowing last week as a mechanism that the system uses for determining how many packets may we receive before we have to send an acknowledgement. Next, we have a checksum, which is used for checking out or used for confirming that data has been received completely without error. Then urgent allows me to identify such things as priority, how fast does this particular segment or packet or segment or datagram need to get through the system. Options, 0 or 32, if any. A lot of times this is used also for padding for the data. And then we finally have the data itself. So this is a TCP header, and the things that key it here are the sequence numbers. Those are the 2 pieces that tell you this is a TCP header. You will not see sequence numbers or acknowledgement numbers in a UDP piece of data. Is what a preamble can? No, it's a preamble is typically used to often synchronize the data transmission. Okay, so no, it's not a preamble here. If you like, why don't we take a look? So the data offset specifies the size of the TCP header in 32-bit words. Okay? That's its purpose. All right.
hey, Jim.
Yeah, George.
Confused about something. Usually when we do bits, we go from left to right. But in this, it chooses over going from right.
Okay, you're fading out again. You always start out great, and then you start fading.
We usually go from left to right.
Okay, I caught it that time. We usually go from left to right. And I agree, but when we're talking about binary digits, okay, we often the digits themselves are numbered from right to left. But when we're talking about data, and we talk about the way we read information, and it's not the same in all cultures, but in our culture, we read from left to right. So the thing that you're going to read first is going to be on the left-hand side, and that's why it's referred to as bit 0. And all the way to the right is bit 32. So in this particular case, I've got bit 0 here, bit 31 here, 32 is over here, 63 is over here, and so on down the line. Does that make sense?
Yes.
So we're not dealing with addressability here at all.
We're not dealing with what again?
Addressability.
Addressability?
Right.
I don't think so. I'm not quite sure how you're using the word addressability. Even when we look at memory locations, often memory locations are referred to in this order.
Okay.
Okay?
Thank you.
All right. All right. Now, here is a UDP header. Okay? Now, both UDP and TCP come out of the same layer of the TCP/IP stack. But you'll notice that the UDP does not have the sophistication of the TCP header. Specifically, it doesn't have the acknowledgement for the sequencing words. Okay? And because it doesn't have that acknowledgement mechanism in place, UDP is referred to as unreliable. Okay? But UDP is also, because it doesn't haul around all that data and therefore does not have that high overhead, UDP is often used when performance is needed. Now, when you're sending data, like raw numbers, like information back and forth, you're going to use TCP because you cannot afford to lose anything. But if you're sending video back and forth, If you lose a frame or something along those lines, it's not a major loss, okay? You may have a little pixelation on your screen and so on, but people are still going to be able to make out the video. So videos and other high-speed type applications often use UDP, and data applications are going to use TCP. All right. So some of the things about TCP and UDP. TCP is sequenced, UDP is not. TCP is reliable, UDP is not. TCP is connection-oriented, and when we say connection-oriented, we mean that there is a back-and-forth conversation going on. UDP, however, does not have that conversation going back and forth in the same way, so it is referred to as connectionless. TCP, in essence, creates up a virtual circuit. Even though the information may not go down the same path between the destination and the host, or the destination and the sender, the important point is that regardless of the path that it takes, there is a circuit that has been set up between these two machines. UDP, however, does not set up any such circuit and therefore allows UDP to provide lower overhead and better performance. Again, TCP uses acknowledgments, UDP does not. And finally, TCP uses windowing flow control, and UDP does not. All right, port numbers. Some of your major applications, and we've talked about this in the past, use standard port numbers. FTP uses 21, Telnet 23, Doom 666, DNS is 53, TFTP 69, POP3 is 110, and News is 119. And this is essentially used to interface your upper layer applications with your transport layer. Again, here are some ports. You'll notice that Telnet is TCP because it's used for transmitting data. You'll also notice FTP is 21, but TFTP is 69. So even though TFTP is used for transmitting data, it uses UDP, which does not provide acknowledgments. So one of the things that you assume whenever you're using TFTP is that, hey, you know, there's the possibility that an error could occur when transmitting this data, and you may have to do it again because there are no acknowledgments with UDP. If you want to transfer things securely to make sure that you receive exactly what was sent, then you would use FTP instead. Okay. All right, the internet layer, or the IP header. At this point now, we're now talking about the network layer. Hey, do you guys want to take a break? And I don't think the Doom port is on the test, Ken. At least I haven't seen it.
I'm good.
Okay. Let me just grab another soda. For some reason, I'm pretty thirsty tonight. 1 second. Yeah, it is that talking. Thankfully, I've got a little refrigerator right next to my desk. No beer, though. All right. So here we see the header. Now, yep, that's all I grabbed, Ken, was just a soda. In fact, I've tried some of these new Dr. Pepper, the Dr. Pepper 10. It's got caffeine in it. One of the things to notice down here is you'll see the data. This is where your TCP header or your TCP or this is where your segment or your datagram is going to go down here. Okay, and it gets encapsulated by the rest of this stuff up here. Okay, so again, going back to the term encapsulation. In either case, you'll notice that there's quite a bit of information here. We have some preliminary setup information, different fields in the top here. The version identifies what version of IP we're using. The protocol identifies the different types of IP protocols. Often we're talking about the different types of routing protocols and so on that are being used. You've got your source IP address. You've got your destination IP address. Notice 32 bits because that's what we need for, at least we need for IP version 4. Then we have our options. And then again, we have our data. All right. So the key here is this is the IP header, and you know it's the IP header. When you see a source IP and a destination IP, that tells you it's the IP header. You're not going to see an IP address in a frame, which is layer 2 data link layer, and you're not going to see an IP address in the transport layer. You're going to see port addresses, not IP addresses. IP addresses are only seen at the IP or the network layer. Okay. Now, this looks very similar to the diagram that we had for the transport layer. Here, notice these circles are above TCP and UDP. These circles are below TCP and UDP, and this is where they identify the protocol that is being used. So when we talk about a protocol number right here, it's going to be 6 for TCP, it's going to be 7 for UDP, and then we've got our IP portion down below. Some of the different protocols, and you'll notice some of the routing protocols in here. One is for ICMP. Then we have IP and IP, which is tunneling, your IGRP, your EIGRP, your OSPF, your IP version 6, and your GRE. You can also have your layer 2 tunnel or L2TP.
And these protocol numbers are all located in the same position in the header?
Okay, I barely caught the end of that. Those protocol numbers are basically stored here in the IP header.
How does it know which protocol is being used, whether it be IP or TCP?
Okay.
Or UDP?
If the packet that is coming out, if that belongs to an ICMP, for instance, a ping, okay, it would use a protocol ID of 1. If, however, the packet contained TCP information, it would have a protocol number of 6. If it was a routing advertisement used by EIGRP to communicate between two routers with respect to the latest routing table updates, then we would identify this packet as using protocol 88. How does that sound, George?
Being an old programmer.
Okay.
So I'm looking for the protocol.
You disappeared again. It's really weird. You start talking, I hear you fine, and then 5 words in, you're gone.
Yeah, I don't think my PC can handle voice very well. Anyways, these numbers are located in the same position on a header, correct?
These numbers are what?
Located in the same position on a header.
I've lost you completely, George. I can't hear a thing.
What position is the protocol number located in? Did you hear that?
I would agree with you, Ken. I don't necessarily think it's his microphone. George, do you want to type it up? What position is the protocol number located in? Okay. Well, one of the very first things that we would have to do is we would have to convert one of these protocol numbers into binary. Now, you'll notice that none of these numbers are greater, okay, than 255, which would be the largest value you could have in a single byte. And you'll notice that our field here, I've got 8 bits or a byte for the protocol ID. So that number would reside in there as a binary value. Let's just pick an easy one. IGRP would be 4 zeros left to right, and then 1001. So 4 zeros, 1001. And that's how it would reside in those 8 bits right here. Does that sound good? How does that sound to you, Ken? Is the protocol number located in the same position for different headers? Well, let's just be clear. When we're talking about a TCP header or a UDP header, which comes from the transport layer, neither of those headers have protocol numbers. However, if you're talking about an IP header is always going to be the same, except that the IP header is going to be used by different network protocols. Okay? Do you recall us ever getting into a conversation as to routing protocols and routed protocols? You know, TCP and UDP are routed protocols. Okay? They are routed by the network layer. EIGRP is a routing protocol. It handles routing. It coordinates routing between routers. But regardless, they all use an IP header. And in every one of those IP headers, the protocol is always located in the third word and starting at bits 8 through 15. Okay, how does it know if it's either a UDP, TCP, or IP? Well, again, UDP and TCP are transport layer protocols. So that information, which is put into a segment or into a datagram, is passed down to the internet layer or to the network layer. And the network layer says, oh, okay, here comes a TCP segment. So because it's a TCP segment, that means that I've got to put an IP header around it. I've got to encapsulate this segment with an IP header, and the protocol number is going to be 6 because it is a TCP segment. Super. Okay, very good. Damn. All right. So looking at some of these, ICMP is a type of message that is transmitted more for utility purposes than anything else. You rarely see ICMP being used for carrying data. And again, it works at the network layer. It is used by IP for many types of things. It's often referred to as a messaging service or a management protocol. And its messages are primarily encapsulated as IP datagrams. ICMP provides hosts with information about networking problems. They are also encapsulated within an IP datagram. So they look like a UDP datagram, okay? And if you recall, UDP datagrams are not reliable. They don't have any kind of acknowledgement in them. All right. Okay, so here's an example of a ICMP message in which the connection between host B and router lab B has been broken or is not functioning. So what happens is host A attempts to communicate with host B, and what occurs is we get an ICMP message coming back that we are unable to contact the destination. All right. Next, let's take a look at ARP. ARP is used to resolve IP addresses to MAC addresses. So what happens at the network layer, the host says, I need to get the network or the Ethernet address for 10.112. And what it does is it basically transmits out, it broadcasts out a message, and it's basically in that message it says, I'm looking for the IP or the MAC address for the system that has the following IP address. That system, 10.112, hears that broadcast, and it says, hey, that's my MAC or that's my IP address. Therefore, I'm going to respond, here is my Ethernet address, and I am going to pass it back to my originating host over here, 10.111. Nice comment, Ken. George's teaching or George's questions and my teaching. Well, I think you can't have one without the other. Whatever the case, I think it works well. All right. So this is how ARP works. And again, it's used to simply say, I've got an IP address. I don't have the MAC address. I cannot communicate at the data link layer without having MAC addresses. So if I don't have a MAC address associated to a given IP address, I've got to go out and I've got to ask for it. And we do that by broadcasting the ARP request out to all of the systems in the broadcast domain. And then the system that owns that IP address is going to respond with its MAC address. All right. Now here's one, our ARP. This goes a little differently. It says, what's my IP address? So what it does is it basically sends out a broadcast saying, hey, this is my Ethernet MAC address. What's my IP address? And the system responding to our ARP requests responds to that and says, your IP address is 192.168.10.3. All right. So now we're going to get in and talk about the different types of IP classes. Today, classes don't do us a heck of a lot, okay? Because in many respects, we've kind of gotten away from classes. And, you know, the different, I guess, boundaries that classes set up. But let's take a look at classes because it's still important to understand what the different classes are. Before we talk about a class, a couple of things. We need to talk about some terms. A bit or a binary digit is one digit with a value of either a 1 or a 0. A byte is 7 or 8 bits. Now, I've never seen anyone say 7, although you can have a byte of 7 bits and what's called one parity bit. Okay? But typically, everywhere you go, if you ask someone what is a byte equivalent to, it's 8 bits or 8 binary bits. Okay. And again, they even mention it here. For the rest of this chapter, always assume a byte is 8 bits. Next, we have an octet, and an octet is nothing more than 8 bits, and it's often expressed as a decimal value. Okay? A network address. This is that portion of an IP address that is shared by all systems in a broadcast domain, or shared by all systems within a network. Okay? And those systems, whether it be broadcast domain or network, those systems are all the same. Okay? A broadcast address is an address that I can send to that has a network address, and then the host portion of the address is all ones. I'm surprised they don't talk about a host address. A host address is that part of the address that is used to uniquely identify the host. An IP address consists of 2 pieces, a network address and a host address. And depending upon the type of address or the class of address, we'll have a lot to say as to where does the network address start and end, and where does the host address start and end. And again, a broadcast address is where the host portion of the address is all ones. And again, the network address is that address where the host portion is all zeros. Okay. Now, originally, when we set up the 4 classes, we basically laid out and set up 4 different groups or classes of IP addresses. Class A, B, C, and then D and E. So there are, really 5, but we really rarely use E because it's for experimental purposes. So anyhow, classes A, B, and C are the ones that are used most often. And by default, we simply set down a standard that said Class A addresses will be set up in such a way that the first 8 bits will consist of the network address and the last 24 bits will consist or comprise the host address. Class B, we said that the first 16 bits will be network address and the last 16 bits will be host address. And then finally, we have Class C, and Class C, the first 24 bits will be network address, and the last 8 bits will be host address. Multicast and research, those are something that are completely different, so we're going to leave those alone. So, a couple of rules with respect to addressing. Network addresses of all zeros is meant this network or segment. A network address of all ones is interpreted to mean all networks. A network address 127.0.0.1 is reserved for testing. A node address of all zeros is interpreted to mean a network address or any host within a specific network. A node address of all ones is interpreted to mean all nodes or referred to as a broadcast address. An entire IP address set to all zeros is used by Cisco routers to designate a default route, and it could also mean any network. An IP address of all ones, same as a broadcast to all nodes on the current network, or sometimes called an all ones broadcast or limited broadcast. So here are the ranges that we have for the different addresses. Class A, that's not right. Oh, I'm sorry, I read this wrong. When we talk about the IP addresses, okay, not too long ago, they basically came up and they said there are going to be those IP addresses which are going to be referred to as public and those IP addresses which are going to be referred as private. The difference between public and private. Public addresses are those addresses which can be transmitted around the internet. Okay, they are publicly known and they are assigned. You cannot simply take a public address and just use it. It must be assigned to you. One of the problems that we had was that we were running out of public addresses. And to avoid this problem or to, I guess, delay its effects, what we did was we set aside a couple of data range or address ranges, and we referred these ranges as private address ranges. And there were 3 ranges that were set up. One for Class A, one for Class B, and one for Class C. And here are the ranges here. 10, 172.16 through 172.31, and then 192.168.0 through 192.168.255. Now, the beauty of a private address is that it does not have to be assigned to you by anyone. You may use these private address ranges at your leisure. If you have a home network, even though a Class A network is a very large network or intended for very large networks, you can use the address scheme of 10.0.0.0 through 10.255.255.255 for your home network. No one cares, okay? The important thing is that you have a router somewhere on your home network that is going to convert these private addresses into public addresses, because your public address is not allowed to traverse the network because it is not a unique address. So somewhere along the line, it must be converted into a public IP address. And most often, George, you are correct. A loopback is not considered a class, but it is considered one of the rules that one should keep in mind when talking about network or IP addresses. And I think that's what they said. Reserved addressing. They didn't necessarily say that it was a class. I apologize if I said that. Okay, so the technique or the protocol that we use for converting between private and public addresses is called NAT. And we've talked about NAT, and we've played with it and so on, so you should probably understand what that term is, network address translation. Again, it converts a private address to a public address or a public address to a private, depending upon which way the traffic is going. Okay. All right. Can you use a public IP address as an internal private IP address? Okay. That's a good question. The answer is yes, you can, but you must do so with care. If you do not convert that public address that's internal to an external public address, if you don't convert it, it will get out there, and we run the potential of having two networks with the same network addressing scheme, which can be dangerous. Okay? Even if you did, yeah, if you did, it could potentially create a problem. So here's the bottom line. The answer is you can, but you've got to make sure that it gets converted in NAT before it's allowed, that data is allowed to continue on to the public network. Does that make sense, Ken? Okay, right? So you shouldn't. Yeah. That would be best practice. You should not. All right. IP version 4 address types. Layer 2 broadcasts, and then broadcasts at layer 3. We also have unicast and multicast, so we're going to talk about some of these. Or I guess we're not going to. A layer 2 broadcast is basically broadcasting on the same network. Layer 3 broadcasts, however, are broadcasting out to multiple networks. Okay? A unicast is when we transmit from one host to another, and multicast is when we transmit from one host to multiple hosts. But this must be defined. It's not a broadcast. Okay? Broadcast goes out to everybody, and we don't even know everybody we're sending it out to. Whoever's out there and hears it, great. Multicast, we already know who this is going to. But we know that this is being transmitted by one system out to many systems that we know of. Okay? All right. I should really come up with a diagram to explain that. Okay. Guys, any questions? All right. Well, let's call it here, okay? And let me remember to turn off the recording.